Good morning and welcome to Cosmic Conversations here in the Morrison Planetarium Facebook. My name is Ryan Wyatt. I'm the Senior Director of Morrison Planetarium and Science Visualization at the California Academy of Sciences. And while the dome is closed, we still want to bring you some cool and interesting people to talk about astronomy. And so today I'm joined by Franck Marchis, who is the Senior Planetary Scientist at
is because if you look at the universe, you see that there is a huge number of possibilities to have life. This is a very interesting picture that was taken in 2004. It's called the Abell Ultra Deep Field. So what the astronomer did in this time, they basically used one of the most expensive telescopes in the world, the Abell Space Telescope, which is a 2-meter class telescope in orbit around Earth, and this new instrument called the ACES, the Advanced Camera, and they stare an empty part of the sky. So when I say empty, it means that there is no stars in this area, and that was the goal. And they observed this for days and days and days. So this image cost a fortune, in fact, if you want to quantify this, because an hour of the Hubble Space Telescope costs a significant amount of money, of course. And why they observe this empty patch of the sky? It was basically because they wanted to see the most distant galaxy, and they wanted to be able to quantify the amount of galaxies in our universe. So what you see here in this ultra deep field those are not stars. Most of those are galaxies that basically emerge quickly after the formation, after the Big Bang. So when a billion years after the Big Bang, basically, we know that matter formed. And what you see here are tiny galaxies very distant. And from these pictures, they basically extrapolate it, and they make a calculation, and they reached a very interesting number. We know that in our universe, there is 2 trillion galaxies. That's a lot of galaxies. So now what is a galaxy? A galaxy is made of stars, right? We know that our galaxy is called the Milky Way. And maybe you have a picture of the Milky Way that you can show.
It's a little bit of an artist rendition, but yes. Yeah,
this is a rendition of the Milky Way based on scientific observations. So the Milky Way is a medium-sized galaxy, 100,000 light years in diameter. I mean, that means that it will take 100,000 years for a photon to cross the entire galaxy. We are located somewhere in the Orion Arm, 2/3 from yes, here. I didn't know that really, but you know that in the Orion. And in this galaxy, but a galaxy is made of stars, essentially. Okay, there is in our galaxy, we estimated that there is 250 billion stars. That's a lot of stars, right? Remember, there's 3 trillion galaxies, so 250 billion stars. That's a lot of potential world. So we are here
in this galaxy. That's a lot,
yeah. We are here in this galaxy, and in a not very interesting place, not too far, not too close. Our solar system is basically as a star, which is a medium-sized star as well. So if you zoom in, you're probably going to be able to see our sun, which is a G-type star. And in orbit around our sun, we have 8 major planets, a lot of asteroids, and so on. So now the question we have is, we know there is life in our solar system. Okay? We know there is life in one specific place in our solar system called Earth. So is there anywhere else in our galaxy, and maybe in other galaxies, a planet like our Earth, a planet which has liquid water, a planet with an atmosphere, seasonal effects, continents, volcanic activity, a moon, a planet which is orbiting in a planetary system with two giant planet like Jupiter and Saturn. So that's what we are looking for right now. That's basically the main motivation of a lot of astronomers in our field, is to find another pale blue dot, another Earth, an Earth 2.0, we can call that. A planet which is identical to our own planet. Why? Because we think that if we find a planet like Earth, it will be very likely that there will be life on this planet as well. Because life appears on our planet very quickly. Our planet is 4.5 billion years old, and we know now that we have proof of bacteriological life which are 3.5 billion years old on our planet. So it means that as soon as we had liquid water, even when the planet was not per se habitable, we have a lot of radiation, a lot of extreme bombardment, and so on. We had this life. So my motivation is, and the motivation of a lot of astronomers, is to find this Earth 2.0. So I mentioned stars, I mentioned galaxy, but I didn't mention other planets, what we call extrasolar planets. Something happened recently. We launched a space telescope called Kepler. That's a NASA mission with a lot of involvement of SETI Institute scientists for the data processing. Kepler looked an area of the sky continuously for almost 4 years. And what Kepler discovered is that the galaxy is full of planets. So when you look at stars, we don't see star per se. You see planetary system. Around us, those stars have planets. And in fact, Abell showed that in average, there is 2 planets per star in our galaxy. He also showed that a lot of those planets are not giant planets like Jupiter and Saturn, but most of them are Earth or super Earth planets. So terrestrial planet probably, like 30% of them, we could roughly. So it means that there's a lot of habitable world over there, a lot of potential places where you could have life and liquid water.
So here we're seeing actually a representation where each one of these icons represents a star with a planet in orbit around it. And as we kind of hover around the Kepler spacecraft here, we're also showing the region that Kepler explored. And as you said, the SETI Institute was critical in analyzing this sort of almost absurd amount of data to find all the planetary systems in this field of view.
Yeah, Kepler looked this area of the sky because there was a lot of stars. And basically, scientists selected 120,000 stars to look continuously. And a lot of them are very similar to our own type stars. But now...
that would be my cat, sorry.
There's a proof of existence of intelligent life on our
exactly,
planet.
Yes. Or at least talkative life, even if not so intelligent all the time.
So now we're launching more interesting missions. I mean, Kepler opened the door of a very important subfield in astronomy, the exoplanetary science. Now we're launching missions like TESS that will look at all the nearby stars to look for exoplanets around them using the same techniques. Let's go to the techniques because that's something very important. Sure. I want to clarify here. Because I did not say that Kepler see any stars, any planets. I mentioned various times that Kepler detected exoplanet. And that's a very important difference. Because in fact, Kepler is not seeing the planet, and TESS neither. Kepler is seeing the shadow of the planet. So it's detecting the attenuation of light due to the transit of a planet. So the planet, it's orbiting around its star.
Yeah, we're going to try basically kind of
small. We're going to see probably here. We're going to see a small attenuation of the dimming. Well, this is exaggerated, but that's basically the idea. We see the attenuation of the light of the star due to the fact that the planet is passing between us and its star. And despite the fact that this kind of configuration is extremely rare, Think about it. We need to have this the line of sight exactly aligned, and we need to be observing at the exact right amount of time. We have discovered 4,000 exoplanets using this technique, even more now, and that's extraordinary.
Primary technique. This is the technique that Kepler was looking at all these stars to look for that little dimming of light.
Yeah.
Yeah.
So, but when you see this dimming of light, you say, okay, there is a planet. If you know the size of the star, you know the size of the planet. And you know the orbit, of course, if you have repeating observations. But that's all. You don't know much about it. You can extrapolate. You can say the star is this temperature. So if the planet is located between this and that area, could have liquid water because the surface temperature will be appropriate for liquid water. We can have an idea of the planet itself by looking at by making comparison with our own solar system, but we don't have information on the planet itself.
And a lot of these planets are very different from ones that we find in our own solar system. So, like Kepler found a lot of these planets that are bigger than Earth but smaller than Neptune. So, kind of puzzling, very different worlds too, right?
And that's very interesting because we don't really know what those super Earth, as you mentioned, are. They are everywhere apparently, but that is not in our solar system.
Yeah.
So that's another kind of very curious thing on our own solar system. So maybe there is something we don't really understand on the formation of planets here. But to go back to to the main point that I want to make here is that we are looking for life, and to find life, we need to be able to get information on these planets, even the super Earth or the terrestrial planets. So how are we going to do this? Well, it's by taking a picture of a planet. So for this, we had some ideas, and this started really in 2002, 2003, with the development of adaptive optics. So we're gonna go in Chile now to basically see the Gemini Observatory. The Gemini Observatory is composed of two telescopes, one in Hawaii, one in Chile in the southern hemisphere. I will go back to that why later on. And this is an 8-meter class telescope, 8.2 meter. So we build those telescopes on the top of mountains here in the Andes because the climate is better. They're far away from cities, so we have better image quality. But we still have have above us the atmosphere. Atmosphere are great for us, human beings, but they are a curse for astronomers. Because if we didn't have the atmosphere, we don't have this blurring effect that we see in all our images. To simplify, the atmosphere is not a completely transparent medium, and it's moving. It's made of layers, okay? And this layer basically move with respect to each other in chaotic behavior. So when the light of the star crosses us, it basically start blurring, this atmosphere start blurring the light. It's like looking through the bottom of a swimming pool outside. You see it blurry. We have the same effect to a lower order with this 8-meter class telescope. So like this is what happens. So the photons cross the atmosphere, go through in the primary that you can see here, the 8-meter class telescope, bounce back to the secondary we just cross, and then after the light go through this hole, and in the bottom and this hole reach you to what we call the focus of the telescope, and this in this case the Cassegrain. And inside this Cassegrain focus we have this kind of cage, and we put here an instrument. That's where we install most of our instruments like camera, spectrograph. So what we installed here in 2014, and this is a project led by Bruce McIntosh from Stanford University, it's the instrument called GPI, the Gemini Planet Imager. You don't see it here because for sake of clarity, we don't have it, but it's basically the size of a mini Austin. It's a blue box. There's not much to see, but inside there is some magical optics. There is what we call a deformable mirrors that move continuously when we do observation to compensate the effect of the atmospheric turbulences. There is a coronagraph that hides the light of the star so you can see the surrounding. So using this combination of coronagraphy and adaptive optics, we get an image quality like if the telescope were in space. And that's really why we're all excited about this technology, because that's allow us to get basically an image with a resolution, with the capability of an 8-meter class telescope in space, even if you don't have yet one, but using this, but from the ground. So this instrument has been used for 4 years. We basically ended the survey very recently. It's called the GPI Exoplanet survey, led by Bruce McIntosh again, and with 100 institutions around the world and 200 scientists. And what we did, we observed 600-ish bright, nearby, young stars visible in the southern hemisphere. And recently, in 2015, we announced the discovery of the first twin of Jupiter. That's what you can see here. So this is the type of observation we get with the GPI telescope. So you don't see the star, it's behind this mask called an occultator, okay, a coronagraph. But you see the sign here indicate the position of the star. And what you can see here at the bottom at 6 p.m. and rotating, it's basically the planet. So this is an image of a planet. It's very difficult to get an image of a planet because the planet is very faint. It's a million times fainter than the star in this case, and it's very close. It's like for the specialists, like 0.2 arc seconds in this case. It's very, very close. The separation, the angular separation, is very difficult here.
And is this purely reflected light, or is this this is an infrared light, or so are we seeing warmth from the planet, or are we seeing reflected light?
So we see both. We see both, in fact. I always say, from my memory, here we have 20% of the light which is reflected and 80% which is emitted by the planet. So the planet is very young. It's 18 million years old, or 80, I forgot. Sorry. This happened. But it's order 20 million. Astronomers are not very... it's way younger than our own Jupiter. Our own Jupiter is 4.5 billion years old. Okay, so here we're talking about like a teenager or even a baby Jupiter, which is being formed. That's why it's very hot. It still have the heat from the formation. And what you see here, so those are photons which are reflected from the star on the surface of the planet, plus the heat coming from the planet itself.
Right.
So this is an image, and that's very key for us, because when you see an image, you can spread the image to get the color, the spectrum. And from the spectrum, we get information such as the temperature, the size, and then we give this information to people who do models, and they're all excited about it, because from this, they can basically tell us more about the planet. So this planet has...
the chemistry of the planet. So is it fine-tuned enough to...
Yeah. So because we have a spectrum in the near infrared, and then we get additional spectrum in other wavelengths from other telescopes, we know there is carbon dioxide and water on the top of the atmosphere of this planet, like for Jupiter. We know from those models that the planet is twice the mass of Jupiter. So it's and almost the size of Jupiter. So it's truly a cousin of Jupiter.
Wow.
We know it's made of band belts from models. We don't know yet. We don't have we don't have an image, of course, of the band belts, but we know from models that it should be made of band belts. We know it's orbiting at 17 AU from its star. And we also know that this system is very complex because it has, like our system, a main belt, and it also has a Kuiper belt. So those are basically fragments of asteroids belt. Okay.
Would you guys like me to bring up the video as well? Would that be helpful?
Yes, please. Sorry, I was supposed to do that, but I have a hard time multitasking, obviously.
No worries. That's what we're here for. So that was the voice of Mary Holt, who's producing this, and I think she can bring up a video of exactly what you're describing.
Yeah, so it's 51 Eridani because it's in the constellation of Eridani, the river that you can see from the southern and northern hemisphere, in fact. It's 100 light years away from us. Okay, so it's very close. So you can see the Kuiper belt. This is the main belt, and it's orbiting just between 16 AU. And this is an artistic representation of the planet. So you can see that we made it with band and belts, and we make it reddish because it's hot still. Of course, this is not a true picture. That's the way we envision it. It's a product of consideration from our professional astronomers plus an artist. Daniel Fitzeler did that in this case. So it's a very interesting result because that's the first time we finally detected C, an exoplanet like Jupiter.
So the interior is sort of like our asteroid belt, and the outer kind of ring is like our Kuiper belt in our solar system.
Yes, that's the Kuiper belt. Yeah,
they kind of like leftovers from the formation of planets. Is this the only planet around in the system, or we don't know if there are others? Or
we don't know yet, and this is gonna be probably one of the first targets that James Webb Space Telescope will observe. In fact, to see if there is anything else around it.
Very cool.
Maybe see. I mean, we have been re-observing it continuously. We did not see any other planets, but we are very close to the limit of detection of GPI in this case. The planet is 1 million times fainter than the star, so it's very like the current GPI reached this limit. And in fact, just an update, we are working on an improved GPI 2.0. That will probably get a better sensitivity and may be able to get lower in better sensitivity, so maybe able to detect maybe smaller planets in orbit around 51 Eridani.
And will still be in the southern hemisphere, or is there plans for GPI on the Gemini in the northern hemisphere?
Yes, GPI, I don't know if it's official, but GPI will probably move to the northern hemisphere to do the same kind of survey in the northern hemisphere. That's the idea, to repeat what we did in the south, but in the north, be able to see most of those, detect those young Jupiter-sized exoplanets. GPI did not only detect exoplanets. I mean, the GPI also detected a large number of disk information around young star system, and detected weird structure in this disk, indicative of the formation of exoplanets. We also detected brown dwarf. There is another survey called SPHERE, which has been doing more or less the same with another instrument at the VLT, and they also detected 2 exoplanets recently. So it's a field in progress. We do have detection of young Jupiter now. We know more about them, but let's go to the next step, which is now we know we can do those instruments. Can we do the same for Earth-like exoplanets? So I mentioned that there is a lot of Earth or super Earth in our galaxy. But in fact, what we're proposing, I don't know, did I lose Ryan? I think I lost Ryan. Ah, you're back. So what we're proposing is to look around us, to target the closest stars in our galaxy. Can you hear us, Ryan?
Yeah, sorry about that. I had to go address a technical issue in my apartment that was going to create some audio problems. So so I'm sorry. I queued us up to talk about Alpha Centauri and Proxima Centauri. So
yes,
that's kind of what we're looking at now.
Let's check out Alpha Centauri. So we have a very young binary star system called Alpha Centauri, made of 2 stars of the same type than the Sun. Rigel and No, not Rigel, sorry. Wow. Tolliman and I'll keep forgetting the official name of Alpha Centauri A, but that's okay. So it's A and B. That's the way we used to call them, and they get the name very recently, and I'm still not familiar with it. So
Yeah,
this is a binary. Sorry?
I wouldn't be able to tell you. So, and
Yeah,
we kind of left those behind. So the sort of, I'll pull away a little bit, but the sort of the kind of brighter star, kind of up in the upper left here, is our Alpha Centauri A and B, and I had actually already started zooming toward Proxima Centauri. So just wanted to clarify
so
that.
A and B are the same size of the sun, okay? And then there is a tiny star, M dwarf stars called Proxima that we're gonna see. Recently, astronomers observed Proxima Centauri using another technique that I'm not gonna go through called radial velocity. They just, in this case, they don't look for the shadow, but they look for the motion of the star induced by the presence of the planet in orbit around the star. So they discovered Proxima B 3 years ago, and a year ago they announced the discovery of Proxima C, another exoplanet that could be in the habitable zone of of Proxima. So this is exciting because if there is terrestrial planet around Proxima Centauri, it may be possible that we have terrestrial planets made of rocks around Alpha Centauri A or Alpha Centauri B, because they form we expect them to have formed from the same cocoon, the same material. And something we discover is that you need to have metallicity, and this metallicity is something like higher than the helium in size, to be able to have planets, terrestrial planets. If you have a low metallicity in the cocoon, meaning that if you have no heavy atoms, then you will not be able to form terrestrial planets. So the discovery of Proxima B and C is important because it's the closest planet, the closest star to us, and there is terrestrial planet there. Is there life on Proxima B and C? Go ahead, sorry.
Oh, I was just going to say, and much like we showed artwork earlier, this is even more hypothetical artwork of what Proxima C might look like, basically just kind of hypothesizing that it could be a rather terrestrial-like world. But this is even more speculative than the image of 51 Eridani that we saw earlier. I just wanted to emphasize that.
Yeah, because in this case, what we know is the mass multiplied by the sinus of the orbit, so it's very unlikely of the planet. So we don't really know much about the planet, even less than in transit in this case. But I should mention there is a very interesting paper that got published by my colleagues in Europe, where they basically use SPHERE, the instrument I mentioned previously, and they claim, but they don't claim, they say there is something interesting which is moving following the same kind of orbit you expect for Proxima B. So SPHERE may have detected Proxima C, may have detected Proxima C. That will be the first picture of an Earth-like exoplanet around Proxima.
Oh, that's amazing.
That will be amazing. It needs to be confirmed, but it's basically the work of my colleagues amazing. They are going to the level of looking at tiny speckles and look at the way they move to basically see whether or not we have detected Proxima B. So let's go back to Earth now. We know that there is very nearby stars, okay? Proxima, Alpha Centauri A and B are very, very close to us, 4.2 AU, 4.2 light years. So together with a team, we have been thinking about how could we image a planet, a terrestrial planet around Alpha Centauri A and B. And this is what we call Project Blue. So Project Blue is a tiny telescope. This is the Abell Space Telescope, a 2-meter class telescope I mentioned. And I think you have a Project Blue schematic. Sorry. It's the size of a mini fridge, okay? So it's very small, 30 centimeter, 40 centimeter aperture. will be equipped with an adaptive optics system to correct for not for the atmospheric turbulences, but for aberration introduced by the deformation of the mirror, and also to allow a better coronagraphy. I'm not going to go through the detail of this, but that's the rough idea, reaching the contrast sufficient to detect a visible, invisible, an exoplanet like Earth. So how are we going to do this? Well, this Project Blue, which is very small, we basically look, it will look continuously Alpha Centauri A and then Alpha Centauri B. I mean, continuously, I'm talking about 10,000, 4,000 hours of observations, and using this adaptive optics system, and then we will analyze the data. That's the goal. So we reach a contrast which is close to the 10 billion, and that will allow us to see, for the first time, in visible light, another pale blue dot, if there is something like Earth in orbit around Alpha Centauri A or B.
So it's actually a little bit like that Hubble ultra deep field that we started with, where Hubble stared at that one part of the sky for a long time, except for this one, it's a smaller telescope that's going to look at our nearest neighbor.
Exactly, and it will look like he has a very narrow field of view, so it will look like very close to the star. And simulation shown that it's possible to do that. This is a project with a lot of different institutions. It's the project still. We don't have funding to launch this telescope. It's a private mission, so that's going to be. We are going to try to get funding from private donors and so on. But this is a goal. What's very interesting here is that we're not talking about billions of dollars. We're talking about $20-30 million to be able to do something like this. And the reason I'm advocating for that is because I think it's going to change radically our view of the universe if we see an Earth-like exoplanet, If we have an image of another pale blue dot, and imagine if we can detect water on it, that will basically change radically the way we perceive the universe. We will know that there is somewhere else a planet that could be explored. And my point is that with this observation will motivate a large community of people to build better instruments. And we're already thinking about those better instruments. I mean, there is a JWST. You have an image that's going to be launched hopefully in 2021. It's a 6-meter 6-meter telescope that is folded. Okay, this telescope will probably bring a lot of interesting results in the field of exoplanets. It's not truly designed for that, unfortunately, because it was designed 20 years ago, especially the instruments. So it doesn't have yet. It doesn't have an adaptive optics system. So it doesn't have a coronagraph that will allow to see exoplanets in orbit around nearby stars. But NASA is already thinking about the next generation. And the next generation are instruments which have code names at the moment called ABEX, Habitable Exoplanets Finder telescopes, that you can see here, which will be roughly 4-meter diameter in size, will be equipped with adaptive optics systems. So with that, we'll be able to reach the sensitivity to detect an Earth-like exoplanet. And then there is a giant, the crazy project that I love because it's crazy, which is the LUVOIR. It's this one I think is an 11-meter telescope, foldable, deployable in space with a gigantic field shield to protect from the light of and the heat from the sun. And this will be equipped with an adaptive optics system as well, a spectrograph and more. And the reports will just come out for those two telescopes, ABEX and LUVOIR. And they show that with ABEX, considering the number of exoplanets we have, that we estimate to have around us, we'll be able to detect, image 100, 200 exoplanets and characterize them. And that's gonna happen maybe in 2040. My point as a scientist here, is a bit political as well, is that it's great to go to ABEX and LUVOIR and have all these crazy and amazing projects that will cost billions of dollars. But considering the time it took us to launch JWST, learning how to do this adaptive optics system in space, learning how to do good science with adaptive optics in space and have an image that will motivate the community is important. And that's why I'm an advocate. I advocate, for instance, the Project Blue, because $20 million to have an image of an Earth-like exoplanet is not much. And I think that will excite this community and also the people, the public. So what we're gonna see, I think you have an artistic view of an exoplanet, right?
Yes, we can actually take a trip to another artist rendition. Let me go ahead and kind of point us
And
in
while
the right
doing this,
direction.
the experts. So we're probably going to have a tiny dot, okay, in the case of Project Blue. We're going to have the color of this tiny dot. And then we can also observe this dot continuously for a long period of time and see how it changes colors over time. And that will basically give us some information about the planet itself, such as the rotation period of the planet. If the planet has ocean and the planet has continental plates, we will be able to detect them. We call that inversion, light curve inversion. So we will not have a pretty picture like you are going to show here, but we will have some strong indication of the existence of water and continents on this planet. And that will motivate the community and young people around us to basically go and explore this planet. You may not go there directly in the next 20 years, but I think having a goal, having a place to explore will basically motivate space agencies, private donors to develop those instruments that will one day deliver an image like this of another world, an Earth 2.0 nearby us. And I don't know what we see. It will be amazing. We will see continents, volcanoes, cities. Why not? We can dream, right? This is something that may happen. And I think that's all.
No, thank you very much. And we may have some questions coming in from our Facebook page or from our SETI Institute page. And in fact, we do. Oh, I see. Question about how close do you think we are to finding an exosolar system like ours?
10 years. If and the reason I'm saying 10 years is because I did not mention we're also building those gigantic 40-meter class telescope on Earth, the ELT, the TMT, the GST, right. And those will be also able to observe the close environment of those nearby stars. Project Blue will also be able to see more than Alpha Centauri. We'll be able to see Regals and other systems, other planetary systems. So I think the only limitation we have at the moment is not the technology anymore. It's the funding. And that's sad, but that's what happened. We are reaching a point for which we will be able to do that for a $20 million for Project Blue, $1 billion for the very large ground-based telescope. So we are building them now, especially the ground-based telescope. So I think that there will be an indication of the existence of life elsewhere in 10 years with those new instruments.
And how clear do you think the signs are for what constitutes a biosignature or something that counts as like a sign of life? Is there a lot of argument and discussion within the community, or is it clear like, oh, if we find this and this, then we've got it?
So I'm one of the reasons I'm advocating to observe Alpha Centauri A and B is because those stars are identical to our star. So if we find life there, it's more likely that the life will be similar to our life, meaning the same kind of chemistry, the same kind of plants chemistry, because they will be using the same type of light coming from the star. Okay, so it's going to be very difficult to convince people that we have found life. So we start looking at very exotic worlds like M-dwarf stars and so on. When we're gonna get those biosignatures or this weird spectrum, I'm telling you there will be a huge arguments in the community to convince each other that we have seen life. But if we find something which is really truly identical to Earth, there will be no doubt. The case closed. We have found life. So that's one of the reasons I think we need to target first G-type stars if we want to get a clear, quick answer on the search for life. Yes,
so
there is discussion.
Stars very much like our sun, M dwarf stars much smaller, dimmer, and redder than our sun. So like the photosynthesis in plants would have to be very different using light from things like that. But so that's what would be challenging. That's really interesting. Do we have any other questions? It looks like we do.
There is a discussion in the community about finding life, different type of life. There is models and so on. People are thinking about it. So it's not something we discarded completely. But my point is that for a quick proof of the existence of life, I think we have to target G-type star, which are like the sun.
And actually, I guess an interesting question, and I'm sorry, we do have a question from Facebook here, we could maybe come back to, but is because you can also look for changes over time, right? Like Earth has seasonal changes as Earth revolves around the sun. So there are kind of different techniques that could kind of add up to more convincing evidence, right?
Yes, so you can, if you look at the biosignatures of Earth, for instance, you will see that they change over time due to the rotation, first of the planet,
right,
and they will change because of the seasonal effect, especially the presence of methane. And then also there is a change on a long scale due to the presence of a civilization. In our case, we are changing slightly the atmosphere composition, so there is more carbon dioxide, for instance. So
right.
An alien species which is slightly more advanced to us, or managed to convince the space agency to build those gigantic telescope 40 years ago, already know we are here. It's very easy. Just look at the Earth, and you see variation of the carbon dioxide. You say, there is a civilization here. So that's why people say, oh, we should not transmit signals around us. I think if there is a civilization slightly more advanced to us, they already know we're here.
It's too late. Well, the other question we had from SETI from Facebook was, what about within our solar system? What do you think the chances are of finding life closer to home?
It's very interesting. There is a lot of search right now, and I think Mars is a prime candidate, not on the surface, but in the caves, because they're protected from radiation. But there is also Enceladus. Enceladus is a very interesting body because we know that he has this kind of geysers at the southern pole. And some analysis of the geyser suggest the existence of what we call a methanosis, something like that. Google it, which is basically a biological reaction that you can see on Earth geysers. Okay. So there is indication of possible life there. This life will be very simple. There will be bacteriological life, probably. I don't think we're going to find insects on Mars or reptiles or stuff like this. I think we will find probably very simple bacteriological life. But I would love to be wrong, by the way.
Very cool. Well, I think we're just about out of time. But again, thank you. And actually, I should thank you too, because the examples you gave of Mars and Enceladus in our own solar system are two topics that we're diving into for our next Planetarium show, which will open in February if everything goes as planned, which of course, right now, nothing seems to go as planned. But those are two of the sites that we're visiting in our virtual trip around the solar system in our Planetarium show. And probably a great topic for something we could do as another cosmic conversation some Friday. So I want to, again, thank you, Franck, for taking part in today's conversation. Thank you to our Facebook audience, both on the SETI Institute page and on our Morrison Planetarium Facebook page. When I introduced our program, I forgot that we're broadcasting on both channels. And so please like both of us, because the SETI Institute is doing some amazing stuff with sharing their content, and I'd like to thank the Morrison Planetarium team is as well. So again, thank you. And
thank you very much. Thank you, everybody. It was great talking to you, Ryan, and thank you, Mary, too.
Likewise. Yes. Thank you, Mary, the person behind the scenes making it all happen. We'll hope to see you on a later Cosmic Conversation every Friday 11:30 Pacific time here on at least the Morrison Planetarium Facebook page.